3 stuff. Just good easy stuff only. Okay, so now we'll move on to something called as replacement algorithms. So we saw, so Dia was explaining about cache in itself, no? So if you see your cache, what if your cache gets filled? Now what will you do? You need to, you still have like your program to run. You need to still access all of your frequently used data. You need to see your temporal locality, spatial locality, all this and that. So how will you ensure that you kick out the correct block in your cache? Okay, so that is why we have like several replacement algorithms. So firstly, we'll look into something called as least recently used LRU algorithm. So this is just like a plain example to understand the gist of it, but I'll show you an actual example also. So let's say your LRU cache unit, your capacity of your LRU cache is 3. So you have only 3 blocks that you can store. So what we are doing is the most recently block, we are trying to store it in the first block, and then least recently used in the last block. So first we have to key 1 value A. So 1 is to A. Okay. Now we are actually putting key 2 to B. Since that is the recently done task, you're putting it at the top because your top should be your most recently used block, right? So now you're inserting C to 3. So that is your recently accessed part. So it's 3, you're mapping it to C. Now if you're getting key 2, so whatever is in the key 2, you're trying to get that value, which is B. So you're actually accessing this. So your 2 is to B will be the one at the top because that is the most recently accessed one. Okay. So now let's say get key 4. So key 4 is not even here. So what do? You have to add 4. So your cache is full now since your capacity is just 3. Now you have to add 4. So 4 will get added in the top, that is your recently used block, and then your 1 will be kicked out. So based on temporal locality, that is, so you will tend to access something that you accessed now. Okay, you'll tend to access something that you access now. So you are just keeping it at the top, and then if at all you need to remove something, you remove the least recently used block. Okay. So that is how the concept of LRU is. So I'll just show you a small example. So let's say in your LRU algorithm, this is your cache. So I'm just naming it as A, B, C, D, your blocks. Okay. So initially it is 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So when A is getting asked, we are just assigning it to the highest value. So what is this? Basically, it's 0, 1, 2, 3. No. So when A is getting called, we are just assigning it a highest value, which is 3. And then we are decrementing all of the others, and telling that these are even more lesser recently accessed than your A, which was recently called now. Okay, now again, if your A is called, that means it still remains 1, 1, but your other things gets decremented. Okay, to just binary normal decrementation. And then when your C is called, let's say 0, 0, the C is called, that means this will become your 1, 1 now. Okay, so this will become your C will become 1, 1, and then the others will get decremented. So what will you kick out? So you will have to kick out essentially the 0, 0. 0, 0, so whenever you have to kick out, so in that case, you have to kick out the 0, 0 part because that is your least recently accessed block, right? So your 1, 1 is your most recently accessed. So you just accessed it right now, and so you're assigning it a highest value. Okay, in terms of binary digits. So is this part clear? It's just based on recently accessed block. Yeah, done. So now we have something called as LFU algorithm. So that's based on frequency. Okay, it's very simple. So initially everything will be 0, 0. If A is called, you just increment it. If again A is called, you increment it. So whichever is called, you just increment it. So essentially you're counting the frequency. So what will you kick out? You'll kick out the least value, not 000, but your least value, right? So like here everything is just 00 here over here. But okay, if at all you need to kick out something from this case, which 00 will you kick out? Because all of these are equal values and the least values, least frequency values. So that is based on randomization. So you just randomly kick out something. So yeah. So but the in LSU algorithm as such, the biggest con is that you need like big counters to actually sit and count all of this frequency. So that's not really feasible. So LRU is the most commonly used one. Okay. So LRU and LFU is clear, right?
Yep.
Okay. Okay. So your cache, no, it tends to have like garbage value initially. So how do you ensure that it is whether that value it's a value or like some random garbage value? So we have something called as tag, no? So this tag that is used to identify which block of the main memory is currently stored in the cache line. So that's what we discussed all this way. Otherwise, there's something called as a valid bit. Okay. So this valid, what does it do is, so if valid is 1, that means there is no garbage tag value. That means a meaningful value is stored. Okay. If the valid is 0, that means the value that is in your cache, in your that block, is actually a garbage value. Okay, that's how it's identified to maintain data consistency. So you should ensure that it's not a garbage value and it's a actual meaningful data. So that you're actually ensuring using this valid bit. All right. This part is clear, no? So this is something what Dia also told. So write back and write through. So so it comes under this concept also. So you have something called as dirty bit. Okay. So okay, let's say if the value is changed in your cache, let's say this A is changed in your cache, how will you ensure that it is also changed in the main memory also? Like every time, okay, here you actually have something called as dirty bit. So if the dirty bit is 1, that means you have actually changed it in your cache. Okay. So when you're trying to kick out A anytime throughout your program, that means so before kicking out A from your cache, we have to update it in the main memory and then you kick out. Okay, so based on your replacement algorithms, you actually decide on which one to kick out. So let's say you're kicking out A, which has been changed some time back. So that time you will check. Okay, let me check if the dirty bit is 0 or 1. If it is 1 now, that means the A has been changed. So I need to change it before kicking out. I need to change it back in my main memory also. So that is the concept behind this. So if D is equal to 0, that means you need not change it in the main memory. So that your time gets saved here. Okay, so you need not change it in your main memory now. Okay, you can just kick out that A if at all you need to kick out. Okay, is this part clear?
Yep.
Okay. So, and then what she told about write through is that both your cache and the main memory just gets changed parallelly. Okay, that's all. That's what cache write is. So now we'll be moving on to our kind of last topic, which is virtual memory. Okay, so why do we have to learn this in the first place? So let's say you have your processors, no? You have like your 32-bit processor, 64-bit processors, and so on. So 64-bit processors, like your word length is 64 bits. So 64 bits gets access from your processor. No. Uh, but in case of your main memory, RAMs and all, you have your 8 GB, 4 GB, 8 GB and all. It's your usual thing. So let's say 8 GB, okay. So 8 GB now, 2 power 3 into 2 power 30. No, G is 2 power 30, that and all is fine. No. So it's basically 2 power 33 bits. So here it's 64 and here it's 33. Okay, so your processor tends to give a bigger address, but it doesn't exist in your main memory because a bigger address which is 64 bits, but in your main memory there exists only 33 bits. Okay, so something called as virtual address is given. Okay, using the memory management unit. So the memory management unit actually converts this virtual address into some existent physical address. Okay, so you have your processor. So from your the processor gives, okay, I told you about main memory, but yeah, from your processor even to your cache also, it gives you a bigger data, if sorry, bigger address, but your cache is of a smaller size. So essentially, it will also have a smaller, less number of blocks also. No, so it has to convert this virtual address into a physical address which is there in your cache using your memory management unit. Okay, so what does this memory management unit consist of is what we are going to look into now also. So yeah, okay, all programs and data are composed of fixed length units called pages. Okay, so actually what did Dia discuss was about your cache and your processor, which was in terms of blocks, right? But if you're talking in terms of your main memory and your second memory, you always call it in terms of pages and frames. Okay, so you in your secondary memory it is called as pages, and the same page in your main memory is referred to as your frames. Okay, so and it's similar to how the block concept works. It's one and the same. Okay, it's literally the same thing. Okay, so all programs and data are composed of fixed length units called pages. So each of which consists of block of words that occupy contiguous locations in the main memory. So it's all in terms of pages. So page cannot be too small or too large. The the virtual memory mechanism bridges the size and speed gaps between the main memory and the secondary storage. So I gave you an example. Uh, like between your main memory and your secondary storage there is a difference, so I showed no, so this your processor and your main memory, just like how it has the difference in terms of accessing the exact address, even it comes to your secondary memory and your main memory, your cache. So it's all so that's why your virtual memory concept comes into picture. So we have something called as page table. Okay. So the page table is what that converts this. It's a part of your MMU that converts your physical address to your to sure, which converts your virtual address to your physical address. Okay. It is actually stored in RAM. 1 second. So the page table, no, is used by the MMU for every access. So it's supposed to be with the MMU. However, since MMU is on the processor chip, and the page table is rather very large. Okay, so only a small portion of it is actually stored in the MMU. So the remain so this page table is quite large. Okay, so but your MMU is quite small because it's on your processor chip. So only a part of it is stored in your MMU. The remaining stuff, that's why your page table is actually stored in your main memory, because you have like much more space to store your stuff compared to your MMU. Okay, so that's why a page table is stored in your main memory. So we know that our page table is stored in RAM because it is large enough to not fit into your MMU, which is in your processor chip, and then it converts virtual address to physical address. So if I have to take my page table, okay, so I have to take my page table from my RAM first. And then again for searching the actual physical address. No, so what do we usually do? We actually find the physical address in the RAM only, right? So after converting from the virtual address or physical address, that also we search from the RAM. So we are trying to access the RAM two times. Like already we are saying that RAM itself is quite slower, so that's why we have cache and all. But when it comes to virtual memory, again we are having this trade-off, and we are trying to increase the access time. No, so our access time is not really efficient here. So in the case of page table, uh, it is in RAM. So you need to first access that page table from RAM, and then again for searching your actual physical address after it is converted from your virtual address, you again tend to access the RAM to get your actual data. So would you not take more time for it? Yes, you would. So that's why we have something called as TLB. So translation look aside buffer. So that's a very small cache, okay? So that's incorporated into your MMU. So it will store the most frequently accessed. It will store the most frequently accessed stuff in your TLB. Okay. So your page table, which is recently accessed, that will be stored in your TLB. So it works like a cache. So it's much faster. So instead of going to the main memory again and again, if you're trying to store something in your cache, that means you tend to access it faster. So we store the recently accessed page table entry in TLB, a small cache. So if data is found in TLB when we are actually trying to find some data, then well and good. But if there's a TLB miss, just like how there's a cache miss, so I mean it's TLB is also a small cache. So if there's a TLB miss, so what do? You first go to your main memory, and then in your main memory you will have your remaining page tables. No, so in that page table you will check if that data is available or not, and if there is any miss in your main memory also, that's called as a page fault. So in your if there's a miss in your cache, that's called cache miss, or here it's TLB miss. If it's a miss in your main memory, that means it's called page fault. So if there's a page fault, then there might be some other page table that's still remaining in your secondary memory. So that also gets checked. And finally, then end of the day, it should be in your secondary memory. Okay, so then you will get your data. Is this part clear, or do you want me to repeat?
I think it's clear.
Okay. So, so if I had to tell just a brief, give a brief, na, the address lines for your processor and your main memory, it's very different. So you need something called as a virtual address. Uh, so that has to be converted into your physical address. So that is done by your MMU, but MMU is in your RAM, so it's not always efficient. I mean, your page table is in your RAM, so it's not always efficient to access your RAM multiple times. So that's why you have something called a CLB, which is a cache. So that will have your most frequently used page table, so you can access it faster. So that's the gist of it. So lastly, like you don't really have your secondary memory for tomorrow's exam. So I'll just tell you like why do we have secondary memory. So we saw about primary memory or SRAM and DRAMs that are basically volatile, no? So our data is lost. But in case of your secondary memory, the data stays forever. And then your primary memory compared to secondary memory is faster. Uh, and then secondary memory is way slower. And then your primary memory is expensive and limited, and your secondary memory is cheap and massive. And your access time also, for your secondary time, it's much more than your primary memory. And then your primary memory, it holds active data for the CPU, and secondary storage, it acts as a digital warehouse. It just stores the value. Here it's just volatile memory and stores the current value only. That's all. So there's like a lot more stories and like pictures on secondary memory. Probably we might have for NSEM, so that time we'll deal with it. So for now, I just gave a brief on it. So is this fine? I think I'm done with it.
Yep.
I took 21 minutes. Yeah. Huh? Okay. Okay. So thank you so much, guys, for staying back.
എല്ലാ
Okay.
PPTs in the 14